Bismillahirrahmanirrahim. I am Dr. Muhammad Wasim, and today I will teach a very important topic of the subject of irrigation engineering, which is called basically the design of impervious floor for the hydraulic structure by using the Bligh's creep theory. So before going into the Bligh's creep theory, I always say to my students that you need to remember the basics. So basics is what exactly something is, why we need that thing, like its applications, and if it has some formulas, then we have to remember it. So before going into the theory, first, why we are studying this topic today? Because when a hydraulic structure fails, there are some possible causes, and out of those possible causes, it's mainly dependent on failure due to piping and then failure due to uplift. So what exactly is piping? When, let's suppose there is a weir and the water is piled up at the upstream side, so the water will start to seep down and then it will move below the structure and will come up at the downstream side of the structure. So during this process, at the downstream end, it will start to erode the soil particles. So what will happen, these soil particles will now progress towards the upstream side. So it is basically a progressive failure that happens at the end of the creep. So now I have used a word called creep. So what is basically the creep length, or the theory is called Bligh's creep theory. So the creep is basically the water particles, the path it traverses from the upstream below the structure and to the downstream where it comes up. The total length is called basically the creep length. We will also try to calculate the creep length for different structures in this lecture later on. So now, if we talk about failure due to piping, it is a progressive failure that initiates at the end point of the creep length. So then, how we can prevent the failure due to piping? It can be prevented by providing an sufficiently long impervious floor below the hydraulic structure. So then there is a question, how long it should be. So when you are designing an impervious floor, its length and thickness, then you will need this Bligh's creep theory. Then there are the further theories like Lenny's theory and Kosla's theory. We will also teach you in the later lectures. So then when the piping starts, then also there is another force, which is failure due to uplift. When the water is beneath the structure, what will happen, that it will try to overturn the hydraulic structure, a weir or a dam or any hydraulic structures. So the uplift force is basically the residual pressure head acting from the underside of the floor and tries to uplift the floor upwards. And what will happen when it will try to uplift the floor? It will develop the cracks and the hydraulic structure will fail. I have used the word residual pressure. Let's say there is a pressure at upstream called H and at downstream it is 0. Like you have provided a sufficiently long creep length. So the total difference in head between the upstream and downstream is basically called the head loss. Let's stay at point A, which is, we can assume that 5 meters from the upstream side where the water particle penetrates into the soil, subsoil. So at that point, a head loss is, let's say, if the total head was 10 meter and a head loss at up to that particular point is 2 meter, then the remaining head, which is basically, let's say in this case 8 meter, is called the residual head. So total head minus the head loss is equal to the residual head, which is the head which is able to cause the damage in terms of piping and also in terms of the uplift force. Now we will move towards the Bligh's creep theory and its assumptions. So now we will try to cover the topic of Bligh's creep theory. So in starting the Bligh's creep theory, Bligh has made some assumptions. So first assumption was the seeping water creeps along the base profile of the structure which is in contact with the subsoil. So what that really means. So here is our representative structure. You can see here is one weir. You can consider it as a, let's suppose, a weir. So there is a water at the stored water at the upstream side. So this is basically the upstream and this is basically the downstream side. So water is stored at the upstream side and it has a head, let's say h, or total depth is h basically. There is a upstream sheet pile of depth d1, then there is another intermediate sheet pile of depth d2, name d2 or depth d2, and then there is a downstream sheet pile of depth d3. The total width is basically the total length is basically the b. So now if we say the first, if you see the first assumption, it says the seeping water creeps along the base profile of the structure. So the water starts to creep in and it moves along the base profile of the structure. The distorted green line is represented by the creep length. So this is the path which is traversed by the water particles from seeping, starting from the upstream and exiting from the downstream side. So the length of the path, the traverse, is called the creep length. So now, if let's say in this case, which is our representative structure, if you have to calculate the creep length, what it should be. So it started from here, so d1 and then it towards the downward side and then the d1 towards the upstream side, because this is the assumption that the water particle moves or creeps along the base profile of the structure. So then 2d1, then 2d2, 2d3, and the total distance b. So here is your total creep length, which is basically L is your creep length, it is b plus 2d1 plus 2d2 plus 2d3, or you can just take the 2 common and it would be, the creep length would be L is equal to b plus 2 into d1 plus d2 plus d3. So now this was the first assumption. So I think you people can remember. Now the assumption number 2. It says the head loss per unit length of the creep, which is basically the hydraulic gradient, is constant throughout the passage. So what is basically the hydraulic gradient? Let's suppose the difference of head here. If you want to calculate the hydraulic gradient from this point to this point, then what we will do, we will take the difference of head between these 2 points. The head is at this point and the head at this point. So this assumption says that the head loss per unit length of creep is constant. It means this is head and this is the creep length. So the head loss, the loss of head along the creep length is constant, right? So we can say the average hydraulic gradient. We can also find the average hydraulic gradient, and hydraulic gradient is what is head divided by the creep length or total distance. So head in this case is our head h, which is loss from over a distance of total creep length, and the total creep length is, which we have already calculated, which is b plus 2 into d1 plus d2 plus d3, who is the same thing. So this is basically our average creep length. So now we have understood the first 2 assumptions. Now the third assumption says that no distinction between vertical and horizontal creep. So in Bligh's creep theory, there was no distinction made between the horizontal and vertical creeps. So like, let's say, it says that the head is dissipated, the water is being traversed along the base profile of the hydraulic structures, and the total head is lost as the creep length is, the head will be more lost as the creep length is more. So we have to provide the sufficiently long impervious floor, as we have studied in the initial part of the lecture. So he didn't made the distinction between the horizontal creep and the vertical creep length. Later on, Bligh has made some adjustment and made the distinction between horizontal and vertical creep lengths, but he said that if the water is moving, if the creep is moving downward or in an upward direction or in horizontal direction, so the head loss over the creep length will be constant, right? So this is basically the meaning of the assumption number 3. So now, according to the second assumption, what was the second assumption? Second assumption says that hydraulic gradient is constant throughout the creep length L. So let's say how we can visually see, or what is the basic physical meaning of this. So this was the basic head, and this is the total head, and this is the total creep length. So the head is lost in a constant manner over the total creep length. So in the initial, I use the word residual head and the head loss. So let's say the head is lost due to sheet pile 1, which is at the upstream side of depth D1. So if I this is the depth and this is 2D1, because D1 is downward side and then D1 is again towards the upstream side, upward side, sorry, not the upstream. So this is the 2D1. So after 2D1, the head loss, so let's say I have to find the head loss for a length of 2D1. How will calculate it? So simply I will take the hydraulic gradient and multiply it with the distance. So the head loss due to upstream sheet pile of depth D1 is head loss, which is basically the hydraulic gradient H over L, and I will multiply it with the total distance, which is 2D1. So it is basically the gradient, which is H over L, multiplied with the 2D1. So same for the head loss due to intermediate sheet pile, the hydraulic gradient H over L multiply by the 2D2, and then same for the downstream sheet pile, the head loss can be calculated by multiplying the hydraulic gradient, which is H over L, with the 2D3. So let's say in this case, so this is the creep length. If I try to make it here, or I can raise this. So now I raise this portion. So here, if I try to mimic, so this is my creep length, the water particle, the distance the water particle has traveled from the upstream side to the downstream side. So let's say it's a string. It's a string, and if you stretch it, what will happen? It will become straight. So let's say I hold this side and this side and try to stretch this string. So what will happen? It will become a straight line. So now this was our total head H at the upstream side, and this is the total creep length, and the hydraulic gradient is constant throughout the creep length. So this is basically the H over L is the slope or the hydraulic gradient. So whenever you try to find the head loss at any point, what you will do, you simply multiply the hydraulic gradient with that distance where you want to find the head loss. So hopefully you have understood all three assumptions, and now we'll move towards the next section of the Bligh's creep theory. So now, as assumption 2, in further explanation of the assumption 2, I will try to explain how the head loss diagrams in the books which you will study, how you can read them, and what is the physical meaning of those head losses and their diagrams shown in the books. So you see, in the previous section, I have explained that the head loss, the head which was total H over the distance L, which is basically the creep length, is constant. So you can see over the whole distance of that thread which we have long stretched, it includes the upstream pile, intermediate pile, and the downstream pile. So we have stretched the whole length. This blue line, we have stretched this thread. So this is the hydraulic gradient line. So now when you see this head loss diagram in the books or in your class notes, you will see something like this. So here what is happening, so this is D1, this is D2, and this is
D3. So what is happening, that this vertical line, this vertical section, this one, this vertical downward line shows that the head loss due to, initially the head was h up to this point h. So now this line shows you the head loss due to the upstream sheet pile d1. So this is the head loss. So last time we have calculated in the previous section that how you will find the head loss due to a particular sheet pile. Then the formula is you just multiply the hydraulic gradient, which is h over l, multiplied with the creep length distance, which is basically the 2d1. So this is the head loss due to sheet pile 1. Then you move towards the sheet pile 2, and between them the slope of this line and the slope of this line is the same. It means that the hydraulic gradient is constant. Maybe it doesn't show the same, but in reality it needs, I have not like, maybe not, I have tried to draw in the same slope, but it may look different. So the slope of this line and this line is exactly the same, because the second assumption says that the hydraulic gradient is constant. So now up to sheet pile D2, so this vertical drop is by the sheet pile D2, and it can be calculated by the hydraulic gradient multiplied with the 2D2, and similarly with the D3, this vertical drop. So it means that the total head is dissipated or lost over the total creep length. So why we need this? Because we want to make our structure safe. And as in the initial section of this lecture, I have said that the modes of failure are due to piping or due to uplift. So when it is piping, you have to provide sufficiently long impervious floor. Then the question is how long it should be, because if we provide a very long floor, horizontal floor, then it would be very costly. So that's the reason that we provide the sheet piles at upstream, downstream, or upstream, intermediate and downstream sides of the hydraulic structures, so that we can reduce the cost and it will also increase the creep length. It's not necessary that you provide the sheet piles. You can provide a horizontally sufficiently long impervious floor, but then it will increase the cost explicitly. So that's the reason that we provide the sheet piles at different locations, so that we can increase the creep length and reduce the cost. So that's basically the reason. And now we will move towards the safety criteria, which are basically for piping and for the uplift according to the Bligh's creep theory. So our aim was, in the start of this lecture, was to design an impervious floor which is safe against piping and against uplift by using the Bligh's creep theory. So the first criteria is now safety against piping. So from second assumption, we have already stated that the head loss is directly proportional to the creep length. So head loss is directly proportional to the creep length. What was creep length? We have already discussed. So head loss H is equal to C, this is the smaller c, multiplied by the L, where C is the percolation coefficient. So this smaller c is the reciprocal of this smaller c is reciprocal is the larger c, which is basically the Bligh's creep coefficient. So now there will be a question what exactly this C is. This C has a different values which you will find from the literature. So if the sediment type is sand mixed with boulders and gravels, so Bligh's has provided its value from 5 to 9, and if it is a coarse graded soil, its value is like 12. If it is a fine micaceous sand, it's 15, and for the light sand its value is 18. So now we can say that the head is equal to 1 over C, which is Bligh. This C is the Bligh creep coefficient multiplied with the L. So if we provide an impervious flow which is with creep length equal to or more than the calculated value of L, so we will calculate this value of L. Then if we provide the impervious floor with a total creep length which is equal to or larger than this L, then this impervious flow will be safe against the piping phenomena of failure.